Knurling is one of those machining black arts that can either make or break the quality of a part. So you would think that given the number of things I've made with knurling on them, I would have the best tool for the job. But alas, I do not. The only tool I have is this 2-wheel bump style knurler. And while it works mostly okay, it does have one major drawback. It puts a ton of side load on the part. This not only makes knurling somewhat unpredictable and inconsistent, but also causes excess wear on the lathe spindle bearings and lead screws. This is a big machine, but it's also a precision instrument and doesn't deserve such treatment. So, I'm making a better knurling tool. While looking for design inspiration, I was perusing Google Images, as one does. I came across the somewhat renowned Marlco clamp knurler design. Aside from having the cool vintage look that I prefer, it seemed to have some very thoughtful design features and also looked very robust. So that was going to be my muse for the planning to come. But then, quite literally at the same time, a generous patron of mine noticed the troubles of the bump knurler I was using. He very kindly offered to send me one of those awesome Hemingway kits of the exact Marlco design I was looking to replicate, and I wasn't about to turn down that offer. Now I'm going to be careful not to show too much detail of this drawing as it's not mine to share, but I will show some of the features as they become relevant for what I'm doing. The tool is made up of 2 main assemblies. One consists of a pair of clamping arms to hold the knurling wheels, and the other is a threaded yoke that moves the arms in and out to adjust the diameter. The idea is that the wheels can be adjusted open and centered on the work in the lathe. Then a cam lever attached to one of the arms forces the wheels together slightly to engage with the work. It's this pinching motion that's the primary advantage of this type of knurler, since it does not put any load on the lathe's bearings and lead screws. And because the arms are allowed to float, it has a sort of self-centering effect, ensuring a consistent and uniform knurling. This will be a lot easier to explain with the actual tool in hand. I've got the drawings, I've got the materials, nothing left really but to get to work. There are honestly a ton of parts to make for this, so for this first video I'm just going to focus on the clamping arm assembly. And even still, there are a ton of parts to make for this in a varying complexity. I'm going to warm up on something that's not too difficult, the side plates. They make up the main body of the knurler and include several holes, some simple milled features, as well as some corner rounds. I soon discovered though that the material supplied is already at the outside dimensions of the drawings, meaning the ugly finish from the steel will be visible, and I'm just not a fan of that. So I'm going to deviate from the drawings just a bit and skim all the faces to get a better finish. Much more acceptable. Next are the holes. Because these 2 plates basically sandwich all the moving components, it's important that the holes on each are in perfect alignment. So to make this easy, I'll draw all the features with the plates stacked. I'll spot drill for each of the different hole locations, then move on to drilling and reaming the 2 corner holes that the arms pivot about. Now I can be reasonably certain that these 2 holes are perfectly in line. The next 2 are for the clamping screws that hold everything together, so I'll drill through both the sides for an M6 tap. All the remaining operations will have to be done separately, so I'll drop the vise stop against my reference edge and remount just the bottom plate. Then chamfer and tap each of these holes. This bottom plate also gets 2 additional holes for a separate tool holder mounting piece, so I'll drill and tap these in this setup as well. Switching to the top plate, I'll chase through the 2 holes, making them clearance for the screw threads, then swap to the 90-degree countersinking bit to form the countersinks for the 2 flathead cap screws. And believe it or not, this bit arrived in the mail literally 5 minutes before I needed it. Talk about impeccable timing. Alright, that's enough drilling for now. Time to mill the rabbets. I'll clamp one of the plates overhanging the edge of the vise and extend the parallels underneath for a little extra support. I've also clamped the other piece in the opposite side to spare my vise any weird clamping loads that could also allow the part I'm milling to drift out of position. With everything secure, I can mill the rabbets over a series of heavy passes, leaving just a few thou on the depth and width for a lighter finishing pass. Alright, that's all the functional aspects taken care of. Time to round these parts out with some, well, corner rounds. A perfect excuse to use the rotary table. Of course, the first step is to locate the table center with the coaxial indicator. I can then mount a sacrificial tooling plate roughly on center, and mill a shallow pocket such that I'll have 2 reference edges to position my parts against before clamping them down. Now I can bring the end mill in and sweep the rotary table through 90 degrees to round the corners. Nice. Because all 4 corners of each are the same radius, I can use the same fixture to work my way through the rest. Then, after a light deburring and finishing with some emery cloth, these parts are looking sharp. Now these were sort of medium complexity parts and they went off without a hitch. Since this next part is much simpler, it should be a piece of cake. This is the spacer block that gets sandwiched between the 2 side plates, and it consists of 2 holes and a rounded end. Simple enough. Much like the first parts though, the supplied stock is right at final dimension. So again, I'll skim these faces, making them slightly undersized but looking much better. With all 6 faces cleaned up, I'll drop the screw clearance holes in here, and of course just slightly chamfer each. So far so good. Next is the round on the end. So again, I think I'll use the rotary table and mill a new pocket for locating the part. I should note that the pocket corners left by the mill are ever so slightly rounded. So to make sure the part fully seats, I filed the edges to give clearance. With everything tightened down, I can mill the 180 degree round just like before. Ugh, well that looks like shit. I must have just messed up the pocket dimensions slightly since the radius seems to be off-center. This will be a completely hidden feature once assembled, but I simply can't allow that kind of work to fly. Let's try this again. Fortunately, this is a super simple part, so I can use a piece of scrap steel to get back to the pre-round state in a matter of minutes. This time around, I'll mill a new fixture pocket in the correct position before remounting the new blank and sweeping the table to cut the round. Really? Again? Oh, here's the problem. The part shifted. Most likely from the cutting forces. Actually, I'll bet that's what happened the first time too, and I just didn't notice. At this rate, I'm going to need a bigger box before the end of this project. For attempt number 3, I'm only going to mill the block to size so I don't have to lose my DRO position on the rotary table center. Then with the blank mounted, I'll cut the round in several lighter passes rather than all at once. This should hopefully keep the forces lower and less likely to push the part out of position. Now that's how that's supposed to look. 3rd time's the charm, I guess. I'll finish this off by drilling the 2 holes, then give everything a nice deburring and test fit on the assembly. Look at that, some actual assembled parts. I hope I got all my mistake making out of my system because these next parts are way more complex. I'm talking about the arms. These have many rounds and fillets, some of which need to intersect tangentially, as well as some slots, and of course they have some holes, both full and partial. So I'm excited to take these on and see if my plan to machine them actually works out. And just like before, I'll skim all the faces to pretty them up a bit before moving on to the fun stuff. And to do all that, I'm going to need another fixture plate, but this one will be a bit more specialized. The first step is to mill a pocket to position the square blanks in. Perfect. Next is to drill several pivot holes to establish the centers of the fillets and rounds. Some of these happen to be on the parts themselves, so I might as well mount one of the blanks and kill 2 birds with one drill. There's 1 on this far end, then 3 on the opposite side, all of which get reamed for maximum precision. That takes care of the pivot holes, but one of the arms also gets the special edge intersecting hole for the yoke mechanism, so I might as well knock that out while I'm set up here. Drills typically don't like breaking through edges, so I'll start by only drilling a smaller starter hole. Then I can jump up to an end mill to clear out the bulk of the material. This doesn't leave a precision finish or dimension either, so I'm only using an undersized diameter for this, which leaves me enough material to take to final size with the boring head. I'll adjust the cutter out until it touches the starting bore, then bring it out just a bit more for the first cut. Then I can start taking passes and adjusting the head out until I'm right at dimension. Alright, that takes care of the fixture plate and some of the features on the arm, but this isn't quite ready to be mounted on the rotary table. I still need a pivot pin. Fortunately, this will be a quick job. I'll chuck up some aluminum bar stock on the lathe, and face and turn the OD to match the bore of my rotary table. Then I can drill and ream a hole to accept the precision ground 5/16 dowel pin, which of course I have to play with for a bit before parting this off to length. Now I can set up on the rotary table. I'll drop my new pin in, then the fixture plate and the partially complete arm. using the precision pin to center it all. With the rotary table dialed into 0 degrees, I'll tram the fixture plate and thus the part square to the mill before locking everything down. The first cuts clear the material forming the inboard fillet, then adding 180 degree sweeps of the table forms the round on the end. That looks perfect. I love it when I can knock out multiple operations in one setup. The next feature to mill is the large curve on the top side of the arm. I'll swap to a smaller locating pin I made on another occasion before dropping the fixture plate on the correct pivot hole. Then remount the arm and use the 5/16 pin again to locate it within the groove. Finally, I'll retram the plate before clamping it down and taking cuts. But just as I begin to do so, I notice I'm suddenly without a DRO. What now? I trace the issue back to the circuit breaker and immediately realize the problem. My air compressor is plugged into the same circuit as the DRO, which is normally fine, but the negative 5 degree Fahrenheit temperatures of Winter Storm Elliott seem to have turned my pump's oil into molasses. So when it kicked on, it overloaded the breaker. I guess I'll just have to suffer without the luxury of compressed air. Fortunately, I have another cooling method I can use. And there is just a tiny bit of air left to help clear the chips. Alright, that's round number 2 complete and it's still looking great. I'll remount on the next pivot hole for the inboard fillet, then start taking passes once again to form this feature as well. Now this thing is really starting to take shape. One more round to go. Literally. This time I'll position the pivot pin on the hole in the end of the arm, then start taking passes sweeping the table back and forth. Since I didn't really do the math to figure out the exact start and stop angles of this round, I'm just winging it, but being extra careful not to go too far. The goal is to get this last round to come out tangent with the fillet and round on either side. About like that. The two arms are slightly different in a few areas, one of which is the size of the back pivot hole. So I'll remount this in the vise, switch to the drill chuck. What the? Oh yeah, no compressed air. As I was saying, switch to the drill chuck, locate the hole with a dowel pin in that drill chuck, then drill and ream this out to the larger diameter called out in the drawing. Alright, there's still more to do on this part, but while I have everything still set up in the mill, I'll make some progress on the second arm. I want to use the same fixture plate, so my first step is to drill the 2 pivot holes in preparation for that. This arm also gets a slightly different hole in the middle for the yoke mechanism, so I'll drop that in here as well. Then I can jump back over to the rotary table and work on the fillets and rounds. First the pivot end fillet, flat and round. Then the large radius on the top side. Except something looks a little off. Yeah, that's not right. Somehow, in my complacency, I drilled this end hole in the complete wrong location. Here you can see the mistake compared to the first arm. Wonderful. I was only kidding before about filling this box on this project, but now I'm not so sure. On the bright side, I had some similar sized stock on hand that I can start over with. Alright, I'm back to where I left off. And a sanity check shows I drilled everything correctly this time. I'll finish this out with the inboard fillet, then knock out the round on the end connecting the two. That's more like it. I just have a couple more operations to do on the ends for the knurling wheel mounting. First will be the slot for the wheel itself. There are a couple ways I could do this, but I'm going to use a slitting saw. It's far narrower than the slot I need to cut, but nothing multiple passes can't take care of. So I'll cut the top first, then the bottom, and after verifying all the distances are correct, remove the material left in between. Perfect fit for the knurling wheel. The second arm goes much the same, only I made absolutely sure to offset the slot to the correct side of the arm. It would be a major bonehead move to mess something up again, especially at this point. The last features are some threaded holes on each arm for the knurling wheel pin retaining clip screws. What a mouthful. With the arm back in the vise, I can use the pin method again to find the center of the hole, then offset the specified distance to drill and tap the M3 hole. And after learning the hard way from my past experiences, I'll use a guided tap wrench on this little guy. If you know, you know. That takes care of all the big pieces, but there are a lot of little bits and bobs needed to get this into a functional assembly. I'll start with the brass bushings. These are a super straightforward design with a press fit tolerance on the OD and a nice slip fit on the ID, which I can achieve with a reamer. I really love turning brass. Too bad that's basically it. But I did get to at least make 2 smaller bushings as well. So I whip those up in the same fashion. Next is the lower arm pivot pin, which looks to already be ground to a precise diameter. I didn't even think to check the fit before reaming the hole in this arm. Nevertheless, all that's needed are a couple shoulders turned on each end of this pin. Simple enough, except I need to remember to take into account the slight deviations I've been making on the fly. Next, I'll knock out the cam lever since I'm anticipating needing it for the next part. It's an even more straightforward part in that it's just a rod with a thread on the end. And being that the thread is so short, I think I'll just form it with a thread cutting die. But first I'll prepare the end of the rod by facing it square and filing a decent lead-in chamfer to help start the die on center. Then when cutting the threads, I'll apply slight pressure with the tailstock to keep everything square. That should do nicely. On to the next. The upper arm gets a shoulder pin as well, but this one is a little more complicated with eccentric ends and a threaded cross hole. The plan I had originally was to use the 4-jaw chuck to position the pin eccentrically while I cut the features. But I only just now realized this isn't going to happen. This is way too small for this chuck. I do have a backup plan in mind, but there are a few steps I have to complete before I can get there. First, I'll face one end square in the lathe, then hop over to the mill where I can mount this part on my square collet block. I'll use the edge finder to locate the center and the end of this rod. Then I can spot face, spot drill, through drill, chamfer, and lastly, tap the cross hole. Now for that backup plan I mentioned. Rather than dismounting this part from the collet block, I'll take this whole thing over to the lathe and mount it right in the 4-jaw chuck. Then I can use the dial indicator to bring it in true by adjusting the 4 independent jaws. Now I need the end of this pin to be eccentric with the major diameter, and the offset needs to be in line with the cross hole I already drilled. Since I never dismounted the part from the square collet block, I know the cross hole is pretty well aligned with the chuck jaws. So I can simply adjust those 2 chuck jaws to dial in the eccentricity that I need. Pretty neat, right? Then I can just start taking passes until I hit the target diameter, which is a slip fit for the bushing I made earlier. After switching back to the collet chuck and parting off the excess length of the rod, I can grip the first end right on the collet and turn this side as well. This almost guarantees that the 2 ends come out concentric to one another. Next up is the lever boss, which is yet another fairly simple piece with a reamed blind hole in one end, a cross hole through one side for the lever arm, and naturally a chamfer on the outboard end. Finally. I'm amassing quite a small collection of parts here, and since I'm a small child, I can't resist testing if it's all going to work together. First, I need to insert the brass bushings into their corresponding holes, which is a simple enough job for the hydraulic press with a soft aluminum block to protect all the finished surfaces. The 2 smaller bushings are for each side plate, and then the slightly larger bushing goes in the top arm. Each of these are only about a 1/1000 press fit, but as it turns out, that's just enough compression to prevent the pins from being inserted. So I'll take a quick trip to the mill and run a reamer through each of the bushings once again to open them back up. Okay, let's put it all together. Nice. The arms pivot very freely, but don't have a ton of side play. And while the eccentric lever arm is slightly snug, I think it will play to my favor when this thing sees some action. The last thing I want to make for this part of the assembly is the knurling wheel hardware, which consists of slotted pins and these fancy little retaining clips. I think I'll start easy with the pins. After first squaring up both ends of the rod stock in the lathe, I'll set this up vertically in the mill with the collet block. Then using the 1/32 slitting saw, I'll cut the 1/16 deep slit near the end, and also do this on the other end of the rod while I'm here. Jumping back to the lathe, I'll file a nice radius on the end, part the pin to length, and radius this side too before repeating for the second pin. The last parts to make are the retaining clips, which will require some very intricate milling on this tiny piece of stock. It seems silly to be using this nearly 3,000 pound machine to make something so small, but with proper setup I'm optimistic it will go okay. To start, I'll get centered up on the rotary table, mill a shallow slot and some tooling plate to match the width of the stock I'm using, drill and tap a hole right in the center axis of the rotary table, then drop my material in the slot and clamp it down on one end. I'll drill a screw clearance hole through the stock, and also add the countersink from the drawing, before securing this end down with the flathead screw provided with the kit. Now I can bring the end mill in to cut the clip to the final width and form the round around the screw all in one operation. After repositioning the clamps a bit, I can switch to my chamfering mill and cut the thin tab that will interlock with the slots I made on the wheel pins earlier. Before parting this off though, I'll take advantage of this all being in one piece and form the second clip on the other end. Then I'll switch to a small end mill and cut most of the way through the tab, leaving just a thin sliver to cut through in a final pass. Doing it this way reduces the cutting forces and the likelihood that the part will pivot around the screw. Parting the second clip is the same process. The last detail on these is a simple chamfer on either side of the tab, which I can shape with a few licks of a file. Then put the final touches on these with the sanding plate. And while I'm here, might as well spruce up the other parts as well. And that about does it for this first part of the build. Despite the few mishaps, I've really enjoyed this project so far. There's a really nice variety of parts in both size and complexity, and each one is like its own riddle to solve, which is half the fun of machining. So I'm definitely looking forward to finishing out the rest of this build and taking a proper knurling tool for a test drive. And hopefully, just maybe, I'll make it through without any mistakes. As always, thanks for watching, and see you next time.